Good afternoon. My topic is using VASPER simulation for the beta sodium trifluoride crystal. The purpose for this project is first, beta sodium trifluoride is normally well known as the host material, especially with the rare earth ion jump ions and conversion materials. Second, we know something about the VASPER as an initial method, and we use the DFT theory to applicate to do the calculation. The critical issue in VASPER is the electron structure building. So for this typical crystal structure I showed here, this shows the high signal sodium yttrium fluoride, and on the corner is yttrium, and the rest is the fluoride, and the inside here is actually one sodium. It's have 50% for each position, so symmetric position. So this item is hard for me to mark. Actually, it's half chance for yttrium and half chance for sodium appears, and thanks Dr. Wang found this paper for me. Give me a chance to say that. So it's a challenge job for us to build the molecular model. So we have to do at least 2 by 2 and by 1 metrics to build a model. And normally in VASPER you should cut a kind of rectangle structures for duplicate. So we developed we create 3 models. One is which sodium yttrium 3, and this double, then goes to 12. So now we're going to see with the calculation result. For the distance, we can see the first line is before the simulation, before the optimization. The second line is after optimization. We can see all the data is consistent very well. And also for the rest of the calculation, this is show the auto number, and we compare the total energy in this line. This is just divided by 2. It's because all is normalized to sodium 3, yttrium 3, and fluoride 12. So especially for the sodium 6 and sodium 12, it's very consistent. So, and also we simulate the optical absorptions here, and we can find the 3 peaks. It's almost at the same position. Well, I tried to find some literature to talk about the sodium yttrium fluoride, the real experimental results, but most of the papers are interested in the doping material. So no one really talks about it. I only found out one paper that taught in this area, this area, the absorption here is from the host material. So that's all I had. Also, as my peers present, I simulate also the ground state, excited state. The result shows here. For the comparison, excited state is the energy is higher than the ground state, as the common knowledge. And also, if any possible electron transfers happen, we can see when add 1 electron to the system, the total energy will be increased. And also, if you move 1 electron from the system, the total energy will decrease. Maybe that gives some idea for if any electron transfer happens, it will the trend for the objects. Also, I did some calculation for the Singlet and Triplet states, which shown here. I'm sorry, I should put side triplet states here. So this is the energy difference, which should for the excited states is minus 96 from last page. Here you can compare the integers like that. So that's give a possibility that the forbidden transfer from triple rate is can through the non-relay energy transfer from the excited single rate state transfer there and have emission. These two figures shows the density of the states of single rate and triple rate. And we heat the system from 0 to 2000 K and see something change. After heat, the total energy goes down, and after that we will continue to do some like molecular dynamics, which I haven't report here. So also we can see the distance change, and also I download the result to YouTube, and on the next page I will show the only. Let's see the bound change, which suggests some position have been moved. It's going to move. This is the show the HOMO and the LOMO charge density. It is supposed to from the HOMO to LOMO. It suggests should be the charge density will be delocalized, but from this picture it's not see very clear. And maybe some suggestion for like bound, anti-bound, something like that. So for conclusion, actually I think we have been create the beta sodium yttrium fluoride crystal successfully. Now I'm working to build sodium 24, yttrium 24, and fluoride 6-8. In the near future, try to add the yttrium and the erbium and the ytterbium and the drop material to calculate the properties for my future research, and show some properties of sodium yttrium fluoride. I think that for the second purpose, I just want to learn what the BUSP can do for us, and try to get some link from the similarity calculation to the real experimental results. That's all for my presentation.
Okay, let's thank the speaker. And the presentation is over.